Okay, so this is the last lesson of the unit, and it's kind of a culminating, kind of puts everything together in a pretty nice way. These are the objectives come pretty close to straight out of the SOLs, and they kind of diverge a little bit from the way the book presents it, but I think we're still going to get out of this what we need. Okay. The one to really pay attention of is the last one. Says, given a polynomial equation, determine the number of real and non-real solutions. In the book, they have where they want you to find the number of positive real and negative real solutions, and we really don't care about that. I mean, the SOLs don't drive us to do that. So we make a little bit of a change at the end just because of that, but for the most part, it's coming from the book. Now, the fundamental theorem of algebra says that a polynomial function of degree n has n complex zeros, including the repeated zeros. So that's important. That's like saying, if it's a fifth degree polynomial, it has 5 complex solutions, right? So whatever the degree is, that's how many it's got. Now, some of those solutions could be coming from a factor which is squared, that has that characteristic look where it's tangent to the x-axis. Okay, you've got to count that as 2, right? But the total will be whatever the degree of n is. How many turning points does a function of degree n have? N minus 1. Those two kind of go hand in hand, right? One of them is for degree, the other is for turning points. So, for example, how many solutions does the equation x to the third plus 5x squared plus 4x plus 20 equals 0? What's the degree? 3. So there's 3. Okay, that's it. That's the whole answer. The answer is 3. 3. So it's 3. Now, you don't know how many are real and how many are not real, but there's definitely 3 zeros. How about now notice, as much as the number, counting the number, notice how they've restated the question. In the first one, it was an equation, right? It was an expression in x equals 0. So they say, what about solutions? In this one, they say, how many zeros does the function have? Okay, because functions have graphs, and then the zeros refer to usually x-intercepts. So, but they're equivalent. We're supposed to know that solutions of an equation are the same thing as zeros of the function. The roots of the equation are the same thing as the solutions of the equation. So the x-intercepts of the graph are the same thing as the zeros. So how many zeros does this second function have? 4, right? 4. It doesn't matter about all those other terms, makes no difference at all. It only matters the first term. And if it's written in standard form, it's the one all the way on the left. That's all you got to look at. So here's your U-try, which we'll just do. How many solutions does that first equation have? I didn't hear you. 4, right, 4. 4 because of that. How many zeros does the function have? 3, right, because of that. Okay. So complex zeros could be real or they could be imaginary. Real zeros can be rational or they can be irrational. So most of what goes on from now for the rest of this lesson is that there's theorems for the rational zeros, irrational zeros, and imaginary zeros. So we're mostly looking at that. I think first is going to come the rational zeros. So here's the rational zero theorem, right? It's a theorem. If you have f of x equals, and a to the n, x to the n just means a sub n is like a coefficient. X to the n means it's an nth degree polynomial. If it has integer coefficients, which, by the way, the SOLs say we should be able to factor over the integers. That's what they mean, that the coefficients of the polynomials will always be integers. Okay, then every rational zero has the form of the following. The factors of the constant term, which is the last term in the expression, divided by the factors of the leading coefficient, right, which is that. So if there are rational zeros, and this is not a guarantee that there are, but if there are, they have to be the factors of the constant term divided by the factors of the leading coefficient. Okay. Good. So here's an example. List the possible rational zeros. Well, okay, first of all, it's f of x equals x to the third. So how many total zeros are there here? There's only 3, okay? And we don't even know if they're all real. You know, 2 of them could be imaginary. Remember, imaginary zeros occur in pairs. But the constant term is 12. So the factors of 12 are 1, 2, 3, 4, 6, and 12. But, you know, you can make a 12 by multiplying 1 times 12 or negative 1 times negative 12. So you'll always have to put a plus or minus in front of them, right? It's never just going to be the positive or the negative. It's always plus or minus. And in this one, because the leading coefficient, it happens to be 1, you know, it only has 2 factors, 1 times 1 or negative 1 times negative 1. Right, so first you write down all the factors of the constant term, then you write down all the factors of the leading coefficient, then you take all the possible combinations of the factors of the constant term divided by the leading coefficient, which in this case, because you only have one leading coefficient, the factor basically plus or minus 1, it's the same list, 1, 2, 3, 4, 6, and 12, which is how many zeros? How many possible rational zeros are there? You know, it looks like there's 12, right? And we know there can be no more than 3. So this is not a list of zeros. This is a list of possible rational zeros. Now, the thing about rational zeros is that ultimately, rational zeros are things you can divide out using synthetic division. So that's why we kind of like to have this list of numbers to go from a third degree polynomial to a quadratic. We could divide out one of the zeros and then use the quadratic formula. Then we got all 3 of them. Right? You shouldn't be trying to copy down every little thing. I mean, some of these slides, this is taken out of the book. Okay? If you really want to write down every little thing, you gotta learn how to take notes. Now, that's a fairly uninteresting one. The next one's a little more interesting. So now, you know, the constant term is negative 10, and the leading coefficient is 4. So actually, we're going to have a lot more combining of things. So the factors of a constant term, negative 10, are 1, 2, 5, and 10. Okay, and they're all plus or minus. And the factors of the leading coefficient are 1, 2, and 4. So we're going to take, you can see how they constructed their list of possible rational zeros. They went 1 over 1, 2 over 1, 5 over 1, and 10 over 1. Okay? Then they switched to the 2 in the denominator. 1 over 2, 2 over 2, 5 over 2, 10 over 2. Right? They're just taking all the combinations. Okay, now move to the 4. 1 over 4, 2 over 4, 5 over 4, and 10 over 4. Okay, that's this list, right? That's this big list right there. But now you can look at that. You can simplify, first of all, like plus or minus 1 over 1 is plus or minus 1. Plus or minus 2 over 1 is plus or minus 2. But also you kind of don't write down things that are actually equal to each other. So we had 2 over 2 is the same as 1 over 1, so you don't have to write that one down, right? 10 over 2 is the same as 5 over 1, so we don't have to write that one down. And let's see, 2 over 4 is the same as a half, so we don't have to write that one. And 10 over 4 is the same as 5 halves. So knock out the ones that are just duplicates, and then that leaves you with this list of possible rational zeros. Now, before we had graphing calculators, like when I was in high school, we used to have to like do synthetic division using those numbers to try to find a zero, right? And then, you know, ultimately, this is a 4th degree polynomial. We were trying to find 4 zeros. But let's see, how many are in this list? 1, 2, 3, 4, 8, 16 zeros, which is quite a bit. But, you know, we would have pages and pages of synthetic division, you know, just going. And if you made a mistake on like the first page, then you were never going to find it. It was right there and you didn't get it right. But that was part of the game. Okay, so let's try these. Right, try them both. The one on the left should be pretty easy because it's got a leading coefficient of 1. The one on the right will have a little bit more. Right, the one on the left, I mean, there's only the factors of 15 to deal with. It's pretty straightforward. The one on the right, factors of 6 divided by the factors of 2. A couple of them repeat. 2 over 2 and 6 over 2, those are repeats, so you don't have to do those. Okay, so when it says find all the real zeros, what's that? Find all the real zeros. The first thing you can do is like use the rational zero theorem to see how many, what are all the possibilities. And this is the book, right, doing this. You don't have to copy all this down. We're going to be here forever if you do that. Just look at the factors of 12 divided by the factors of 10. And you could see, how many is that? That is 1, 2, 3, 4, 5, 6, 10, 14, 16. And now they're all times 2. So it's 32 different possible rational zeros. In fact, how many total complex zeros are there? 4, the degree of the function, right? So not all these are going to work. In fact, maybe like almost none of them work. So, you know, we could just start, you know, doing synthetic division 32 times. But the fact is, we do have calculators now, and we might be able to narrow this down by look at the graph. Right? That's the graph of this function. And how many zeros do you see on that? It looks like there's 4. Now, we don't know if they're real. I mean, they're clearly all real, okay? We don't know if they're rational or irrational. But if I had to estimate, it looks like, you know, there's something in between -2 and -1, right? That could be -3/2. There's something in between -1 and 0, and then 0 and 1. That could be something like ±1/2 or ±3/5. And then there's something in between 2 and 3. And actually, the only number there could be 12/5, right? So that's just trying to narrow it down. It can't be any of the rest of those numbers because we can just match them up. So now we're down to actually, for the plus or minus, that is ±1/2. We're only looking at -3/2. It could be ±3/5. Those are close to 1/2. And then the 12/5 is only a plus, if it's that. So let's go to the next slide. And now I just wrote down those possible zeros, and we're going to try to use synthetic division, right, to see what works. So, you know, I know where this is going, but I'm just going to repeat what I did in the last class, which is I'm going to start with +1/2. I mean, it looks like it could be +1/2. +1/2 is positive. So in doing the synthetic division, there's less issues like with multiplying negative numbers and things like that. You know, 1/2 is easier than 3/5. So let's try that. Remember how we do synthetic division. First, I write down the coefficients, right? Are there any missing powers of x? No. What do you do if there's a missing power of x? You put a 0, right, as a placeholder. Okay, then we're going to go 10, -11, -42, 7, and 12. Okay, now if I'm trying to check 1/2, remember 1/2 is the 0, and that's what we put in that bracket. We didn't put in, if it said x -1/2, we put in +1/2. So we want to stay positive. Okay, then we bring down the 10, and we start to multiply. Now, how will we know if 1/2 is a 0? What will it look like when we get to the end? The remainder is going to be 0, right, if it works out. So let's try this. 1/2 times 10 is 5. Add. 1/2 times -6 is -3. Add. 1/2 times -45. That stinks. -45/2. Yeah, I'm going to finish this out, but in my mind, as soon as I'm sure that it's not going to have a remainder of 0, I really don't care anymore. But, okay, 7 would be 14/2, so that'd be -31/2. And then 1/2 times -31/2 would be -31/4. And 12 would be 48/4, so that's 17/4. Right, so the remainder does not equal 0. That tells you 1/2 is not a 0. Well, if it wasn't 1/2, then I'm thinking it's got to be 3/5. I mean, if there's something in there, 3/5 was also in between 0 and 1. So let me try this again. Write down the coefficients: 10, -11, -42, 7, and 12. And then in the bracket, I'm testing 3/5. Okay, and I draw my line. Bring down the 10. So 3/5 times 10 would be 6. If you're not sure, use your calculator. -11 plus 6, -5. Okay, 3/5 times -5, -3. Add. Okay, that worked out. 3/5 times -45 should be, 5 goes into 45 9 times, so -27. Add. And 3/5 times negative 20, negative 12. Add, you get 0. Hooray, we found a 0. Okay, so this is a 0. Okay, now remember, when you do synthetic division, we're not only finding the 0, but we just reduced the polynomial from a 4th degree polynomial to a 3rd degree polynomial. Okay, now we still need to see whether we can find another 0. And I'm pretty sure I remember this from the class before, but I think it's negative 1/2. So I'm going to use negative 1/2 as the 0. Normally when you do that, just do it on that row of numbers that you just created. You don't have to don't write down all the numbers of the quartic that we started with. You know, just use the cubic that we've got in front of us. Now let's put in negative 1/2 and draw our line. Bring down a 10. Negative 1/2 times 10 is negative 5. Add. Negative 1/2 times negative 10 is 5. Add. Negative 1/2 times negative 40 is positive 20. Add 0. So we found another 0. Negative 1/2 is a 0. Now, what we've got left is a quadratic, right? We went from quartic to cubic, and now this is 10x squared minus 10x minus 40. So essentially what we're doing now is we're trying to solve that equation. And the thing is, we don't need to test a bunch of rational zeros anymore. Now we can just use quadratic formula. And that'll find, even if they're not rational zeros, it's going to find it. So let's do that. 10x squared minus 10x minus 40 equals 0. So what's the first thing we should do to simplify this? Divide out a 10, right? So it's x squared minus x minus 4 equals 0. So is that factorable? Remember, if it's factorable, since it's a 1x squared, it's got to be that there's factors of negative 4 that add up to negative 1. Are there factors of negative 4 that add up to negative 1? No, so it's not factorable. That means you're going to have to use quadratic formula. So here's the end of it, right? X equals negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 4 to all over 2 times 1. So x equals 1 plus or minus the square root. Okay, this is going to be 1. Okay, minus 4 times 1 times negative 4 is like saying plus 16. So that's the square root of 17. All over 2. So the last two zeros are actually irrational. In fact, let me write them like this. That means 1/2 plus the square root of 17 over 2 and 1/2 minus the square root of 17 over 2. What do you call two numbers that the only thing different between them is the plus and the minus in between those? What do you call it when the only thing different is the plus and the minus? We did this before. Starts with a C. Conjugates. They're conjugates, right? That's what the quadratic formula always produces, are conjugates. Okay. Which leads us to, nope, not yet. We'll get to it next slide. So on this one, I'm not going to run through this whole problem, but it says find all the zeros of this function. Okay, well, how many zeros can you see on the graph? But one of them is a repeated, right? Which one of them is actually repeating? How does it look like on the graph when it's coming from a factor which is squared? Remember this kind of thing right there? That tells you that it must be coming from something like this, x plus 1 squared. The other one, since it goes right through the x-axis, that's coming from x minus 2. Now, that would give us 3 zeros, and there might be 2 left. So we could do synthetic division. In fact, let's just do that anyways. I think we got the time. So let me write down, it's a 5th degree. We're not missing any powers of x. So it's going to be 1, negative 4, 4, 10, negative 13, and negative 14. So first you divide out a negative 1. Bring down the 1. Negative 1 times 1, negative 1, negative 5. Negative 1 times negative 5, positive 5, 9. Negative 1 times 9, negative 9, add. Negative 1 times 1 is negative 1, which is negative 14. And then negative 1 times negative 14 is 14. So we got a remainder of 0, which we expect. Right. Okay, now let's take out another negative 1. Bring down a 1. Negative 1 times 1, negative 1, negative 6. Negative 1 times negative 6. Negative 1 times 15. Negative 1 times negative 14, which is 14, 0. Okay, got the one last 0 is 2, so let's divide that one out. 2 times 1 is 2. 2 times negative 4 is negative 8. 2 times 7 is 14, 0. So we divided them out. Every time we got a remainder of 0, that's how you know that there was a 0. We went from a 5th degree polynomial to a 4th degree to a 3rd degree and finally to a quadratic. X squared minus 4x plus 7. And you would have to solve that to get the last 2 zeros. And is it factorable? Are there factors of 7 that add up to negative 4? No. So it's not factorable. You would have to put it in the quadratic formula. Okay. And I think if we just did the discriminant, you would see negative 4 squared minus 4 times 1 times 7. Right? That's going to be 16 minus 28, which is negative 12. What does that tell you about those last 2 zeros? They're imaginary, right? We would have imaginary zeros. Okay. So now these are the 2 last theorems. Complex conjugate theorems and the irrational conjugates theorem. Right? One of them is saying, like this one here, that if you have, let's say, 3 plus 7i is 1 0, that you must also have 3 minus 7i. You have to have the conjugate. Right? The irrational conjugates theorem is saying if you have 3 plus the square root of 7, then you must also have 3 minus the square root of 7. Right? Because in the end, where do these i's and square roots come from? They come from right there. And what's right in front of the square root? Plus or minus. So you're never just going to give 1. Not as long as they said here, that we have, they're saying real coefficients, but that's not exactly, okay. Notice that at this one, the first one, they say the polynomial has to have real coefficients. Here they're saying it has to have rational coefficients. You know, if you have square roots as coefficients, okay, well now you can just get 1. But in fact, we're only responsible for factoring, as the SOL say, over the integers. Over the integers means integer coefficients. It doesn't mean that you don't factor and sometimes get a fraction involved, but the coefficients are always integers. Okay, so this is the kind of problems we get with that. And this is worded kind of strange, and one thing is definitely left out, and that is that you should say that we're trying to write a polynomial in standard form. Because if you're going to write it in factored form, that would be very easy. Okay, so the first one, the number 5. This gets to the relationship between zeros and factors, right? If there's a 0 of negative 1, what was the factor that it came from? X plus 1, right? Remember, if the factor is x plus 1, then negative 1 is the 0, because that's what you plug in to x and get 0. Okay, then what are the factors that come from the zeros of 2 and 4? X minus 2 and x minus 4. So what they're asking us to do now is, okay, multiply. So how did we multiply 3 factors together? Take 2 of them and then do the other, right? So let's say I do, I'm going to do the last 2 first. That's always my favorite. X squared minus 6x plus 8. And now I've still got a factor, multiply by x plus 1. Okay. How do we multiply 2 terms times 3 terms? The grid. Probably I mean, you could do the vertical format that they showed in the book, the horizontal format, or the grid. I'll do the grid. That was terrible. Okay, so that's x plus 1 and x squared minus 6x plus 8. So just fill in the grid. X to the third minus 6x squared, 8x, x squared, negative 6x, and 8. So all that together gives us x to the third minus 5x squared plus 2x plus 8. So, I mean, the truth is, now if I multiplied all that by a constant, it would still have all the same zeros. But that's why they say the leading coefficient has to be 1. Or I could multiply by another factor. You know, I could come along, what if I multiply by x minus 4? Right? It would have all those zeros, and then 4 is another 0. That's what they're saying has the least degree. So just do these 3. Don't make it any more complicated than it could be. Now, for number 6, notice they've given us 1 irrational 0. So it's got to be, irrational zeros come in conjugate pairs. What's the other irrational 0? There got to be a 1 minus the square root of 5, right? So when you see, if it's missing 1, you have to fill it in. Otherwise, it's not going to work out at all. Okay, now we got to turn those zeros, even with the square root in it, into factors. So how do you go from the 0 to the factor? What's the factor that comes from a 0 of 4? X minus 4, right? It's always x minus the 0. So then the next one will be x minus, parentheses, 1 plus the square root of 5. And the next one should be 1, oh sorry, that's wrong. X minus 1 minus the square root of 5. Now, you could, in those last two factors, you could distribute the negative, right? That'll flip the sign to both terms. And then you'd have a 3 by 3. And you can make a grid that has, 3 rows and 3 columns, and then fill it all in. What would happen is, because these are conjugates, it'll cancel all the square roots. But there is an easier way to do this, which goes like this. If we're saying that we have zeros that are x equals 1 plus or minus the square root of 5, okay, then we subtract 1 from both sides. X minus 1 equals plus or minus the square root of 5. And then you square both sides, right? X minus 1 squared equals plus or minus the square root of 5 squared. Okay, well, x minus 1 squared is x squared minus 2x plus 1. What do you get when you square plus or minus? If you square a plus times a plus, it makes a plus. A minus times a minus makes a plus. So the plus or minus goes away. When we square it, there is no more plus or minus. And then the square root of 5 times the square root of 5 is 5. Okay? There you go. And so now subtract 5 from both sides. X squared minus 2x minus 4 equals 0. So actually, if we multiplied those last two factors here, that's what we would have gotten. So we still have to multiply x minus 4 times x squared minus 2x minus 4, which I'm not going to do because at this point it just becomes an exercise in what we already know how to do. But the 2 points are, number one, if you only get one of a conjugate pair, you have to fill in the other of the conjugate pair, even for irrational conjugates. And then you got to somehow be able to figure out what was the quadratic that produced those two. Okay, let's try this one. Number 8. What's the missing root 0? 3 plus I, right? You can't just have a 3 minus I, you got to have a 3 plus I too. So now we need to turn those into zeros. Remember, factors. Factors are always x minus the 0. So this is going to be x minus 3, x minus 3 minus I, and x minus 3 plus I. Again, you could distribute the minus and make a 3 by 3 grid, or you can do this. X equals 3 plus or minus I. Subtract 3. X minus 3 equals plus or minus I. Square both sides. X minus 3 squared equals plus or minus I squared. X squared minus 6x plus 9 equals, what do you think you're going to get if you square plus or minus I? Okay, well, what does I squared equal to? Negative 1. So the plus or minus goes away because you squared it, and I squared equals negative 1. So now we add 1 to both sides, and we have x squared minus 6x plus 10. And then you would still need to multiply by x minus 3. Almost done. Ready? Okay. So what are the two missing zeros on number 7? Negative 2i and 4 plus the square root of 6. So we're not going to take it through, but you know now how you could turn those into factors and, multiply to get the polynomial. One question that could be like this. What would be the least degree of a polynomial which has these 3 zeros? And you would say 5, because you got to throw in those other 2, right? It has 5 zeros now. It must be a degree of 5, at least. Okay, and then this is the last thing, which is, and in the book this is where they're trying to get us to use what's called Descartes' rule of signs to come up with the number of positive real and negative real zeros, which is actually not what we've been asked to do for the SOLs. What we've been asked to come up with is like the possible number of real and imaginary. Now the one thing that's of no dispute is how many complex zeros can this function have? Here's the function. How many complex zeros does it have? It has 6, right? Whatever is the degree of the highest power term, so 6. So imaginary zeros, according to what we learned, they come in pairs, right? You can't have just one. It has to come in plus or minus numbers. So, what are all the even numbers less than or equal to 6? How about 6, 4, 2, or 0? Okay. Now, if there's 6 complex zeros and all 6 are imaginary, then there's no reals. Right? If 4 of them are imaginary, then how many reals? 2. You just subtract. If 2 of them are imaginary, there's 4 reals, and if none of them are imaginary, then evidently all 6 are real. Now this one, if you look at the graph, how many zeros do you see there? Yeah, you definitely see 2. So there's no way that it's going to be this first line. I could definitely take that out as a possibility. But the others I really don't know. Remember that the behavior near zeros, the same one that tells us that if it's raised to an even power, it's tangent to the curve, tells us if it's raised to an odd power, not just the first power, it goes right through the x-axis. So there's no telling that like one of these could be there 3 times. It would still have that look, even though it was there 3 times. So that could be 3 real plus 1, there's 4. Or what if both of them were there 3 times? From a factor raised to the 3rd power. Then all 6 of them are real. And none of them are imaginary. So you don't know for sure unless you just like use what we've done before this to find all the actual zeros. Okay, try. Determine the possible numbers of real zeros and imaginary zeros. So make a table. Complex, real, and imaginary. Right? In the first column, you're going to put the number of complex. That one does not change. Yeah. Yep. That one does not change. Then you got to come up with the number of imaginary. What do you know about the imaginary zeros? It's an even number. So it must be an even number less than the number of complex zeros. And then the number of real zeros is the difference. How many complex zeros? 3. How many possibilities for imaginary zeros are there? 2 and 0. So how many possibilities are there for the real zeros? 1 and 3. That's it. Remember, for a 3rd degree, this is a cubic, the leading coefficient is positive, so you know that it has a shape of a graph that looks something like that. You know, which means it goes infinitely up and down. There's no way that it can avoid crossing the x-axis at least once. And that's why the least number of real zeros is 1. Got to be 1. Could be 3, but there's got to be 1. Okay, let's do this one together. Just complex, real, and imaginary. Right? So how many complex zeros does this have? 4. How many possibilities are there for the imaginary zeros? Could be 4. Could be 2. Could be 0. 4 and 4. So how many real zeros? Could be 0. Could be 2. Could be 4. Right? How could you narrow it down? You could graph it, look for the x-intercepts. You know, if you saw something like this, right? If the graph looks like this, you know, we know what the shape of one of these graphs is. So what if it was like that? How many real zeros? There's 4. So you would know that you're dealing with that case. You know, it would have to be that one. But it could also be the case, it could look like this, right? It could be that on one side it dips down and there's your 2 zeros, but then the other turning points are actually keep it above the axis. There's your 2. Or the last possibility is that it's actually all above. What if it was like this? You know, something like that. How many are there? It's actually 4. You got to count the repeated zeros because they just touch the x-axis and go back the other way. That's actually, there's 2 there and there's 2 there. That's 4. Okay. And that was it. So define a polynomial function given its zeros. Right? Determine the factored form of a polynomial expression from the x-intercepts of a graph. Describe the relationship between the roots of an equation, the zeros of a function, the x-intercepts of a graph, and the factors of an expression. And given an equation, determine the number of real and non-real solutions. Looks pretty thorough.